This is a picture of a gas. You'll notice there are very few molecules for the space. The molecules are always moving, and they're colliding with the sides of the container and with each other. There are essentially three variables that we need to work on here: pressure, temperature, and volume. Let's think only about pressure and temperature, keeping the volume constant. If I raise the temperature, then that means the molecules start to move faster. If the molecules move faster, then they hit the sides of the container more often. And if they hit the sides of the container more often, the pressure will increase. So pressure and temperature are directly proportional. As one goes up, the other also goes up. Now let's think about pressure and volume. If I keep the temperature constant and increase the volume, then you'll notice the molecules have to move farther to collide with the sides of the container. So the pressure has gone down. If I decrease the size of the container, then you'll see there are more collisions and the pressure has gone up. So pressure and volume are indirectly proportional. As one goes up, the other goes down. Now let's think about volume and temperature. We keep the pressure constant. If we keep the pressure constant as I increase the temperature, notice how the volume is going up. That's the only way to keep the pressure constant, is if the volume goes up as the temperature goes up. If I decrease the temperature, the volume goes down. Because again, that's the only way I'm going to keep the pressure constant. So temperature and volume are directly proportional. As one goes up, the other goes up. As one goes down, the other goes down. All of those relationships between pressure, volume, and temperature that we just talked about can be written in the form of this equation. Pressure times volume over temperature equals some constant K. You'll notice this does reflect all of those relationships we just talked about. If pressure goes up, volume has to go down in order for K to stay constant. If pressure goes up, temperature has to go up in order for K to stay constant. If volume goes up, temperature has to go up in order for K to stay constant. Now, we really don't want to do this equation because we have no idea what K is. So where this equation is going to be useful is if we have pressure, volume, and temperature changing, so that we have two sets of these variables. We have a pressure 1, a volume 1, and a temperature 1. We also can write a second equation, pressure 2, volume 2, temperature 2, and those would also be equal to that very same K, which means we can write an equation, pressure 1 times volume 1 over temperature 1 equals pressure 2, volume 2 over temperature 2. This is called the combined gas law. Another way to write it, which gets rid of the fraction so it might make you feel better about it, is pressure 1 times volume 1 times temperature 2 equaling pressure 2 times volume 2 times temperature 1. Notice the switch in temperatures here. One thing we do have to talk about here is the units. Pressure can be in any unit as long as pressure 1 and pressure 2 are the same unit. So atmospheres is a pressure unit, torr is a pressure unit, millimeters of mercury is a pressure unit, pascals is a pressure unit. It doesn't matter which of those pressure units you choose, but P1 and P2 have to be the same unit. Ditto for volume. Volume could be liters, volume could be milliliters. It doesn't matter, but both volume 1 and volume 2 have to be the same unit. Now, temperature does matter. Temperature has to be in a scale called kelvins. The advantage of the Kelvin scale is that there is no such thing as a negative temperature in Kelvin. The lowest temperature it is possible to reach in the real world is 0 kelvins. And you can see where this would be an advantage, because then you don't end up with negative volumes or negative pressures. The nice thing about kelvins is the conversion between Celsius and Kelvin is very easy. It's degrees Celsius plus 273 equals Kelvin. And that's all you have to do.